Howie, our speaker. She's been teaching here at JC for 25 years, total of 30 years of teaching, 5 years or other places. Her goal throughout her teaching career has been to help students see the beauty in mathematics and to hopefully help them enjoy math, a field which is typically difficult for a lot of students. She studied at California State University, Santa Claus, and she also went to Calvin College, which is in Grand Rapids, Michigan, and Western Michigan University. Her hobbies include reading, both fiction and nonfiction, prose and poetry, appropriately enough, playing piano, playing the pipe organ, which is a new venture for her. She began taking lessons in that instrument recently, and playing games of all sorts, video games, card games, and board games. So I'm going to introduce our speaker, Heidi Meyer Fernandez.
So, thank you, Denise. As Denise shared, I do teach mathematics here, and it is my goal to help students to enjoy mathematics and to be able to, just find mathematics accessible and approachable. So, actually, this talk comes out of that desire of mine. In my 30 years of teaching, I have so often had students come up to me and say, oh, I get straight A's in all my English classes, and I can't pass a math class to save my life. What's going on? And I would say, well, math and poetry are so similar. And the students would look at me like, what are you talking about? And on the spot, I couldn't put that sense that I had just into words and explain that really, really well. So in order to do that, I thought it through, and I pulled this talk together. So I see Denise is coming around with a handout. I have so many ideas, so many concepts that are going to be coming at you really quickly during this talk. So on this handout, what you will see is what I find to be the 5 major connections between mathematics and poetry: playfulness, pattern, power, elegance, and surprise. And so you'll have those in front of you all the time in case you kind of get lost in the details. I also want to encourage you just to sit back and enjoy. And if there's something that you don't quite catch or you don't quite understand it, that's okay. I've provided also some resources on that handout that you could look into if you'd like. Also, you've got my email address here. If you'd like to email me with a question, that would be fine too. So just take this kind of lightly as we dance over topics pretty quickly and we don't delve into anything too deeply. There will not be a test. Okay, there's not a test, so just feel free to enjoy. So I am a mathematician, but my first love is actually poetry. And it was when I was in high school that I came to love poetry, and I had this idea that poetry was really, really romantic. It was very deep and romantic and serious. And I imagined falling in love, and I thought that when I fell in love, the man I fell in love with would, of course, read me poetry. Well, I finally did fall in love, but after about 6 months, this guy hadn't gotten the idea yet that he was supposed to be reading me poetry. So finally one evening I said to him, Dave, it would just be so meaningful to me if you would read me some poetry. And to my surprise, he got up off the couch, walked into the other room, and grabbed a book. So I was so excited I closed my eyes. This was going to be the highlight of my life. Very, very excited. So he came back in, opened a book, and began to read. They've put a brassiere on the camel. She wasn't dressed proper, you know. They've put a brassiere on the camel so that her humps wouldn't show. And they're making other respectable plans. They're even insisting the pig should wear pants. They'll dress up the ducks if you give them a chance, since they've put a brassiere on the camel. Well, I learned a number of things that night, only one of which applies here, and that is that not all poetry is deep and romantic and serious. Some poetry is quite playful. That poem was by Shel Silverstein, who did a lot of writing for children. But there are also forms of poetry that are also just intended to be playful. One of them is the limerick. There was an old man of the Dee who was sadly annoyed by a flea. When he said, I will scratch it, they gave him a hatchet, which grieved the old man of the D. So, just kind of silly and playful. Any poem that's written in that form is intended to be playful. So you might think, well, sure, poetry can be playful, but math? Are you kidding me? Think about it a little bit. If you look around, if you just open a newspaper, you'll see ken-ken, Sudoku, just all sorts of number puzzles and logic puzzles all over the place. So far, the playfulness that I'm talking about is actually pretty light. And I want to start this talk out quite light. I don't want to go for the depths yet. So that's clearly not the deepest connection between mathematics and poetry, the fact that they're playful. I think any field can be playful, right? Go to chemistry, you can do some really cool experiments. What about art class, music class, PE class? Those things can be really playful or really fun. So I want to go just a little more deeply with the play and talk about the concept of infinity. Kind of a concept that can tickle our minds a little bit if we think about that a bit. So human beings thinking about the infinite goes back at least as far as Zeno of Elea in 450 BC. And I probably should have warned you guys about this before you came in, because you can never leave this room. I have an entirely captive audience, because you see the door back there? Before you get to that door, you have to get halfway to that door. But once you hit the halfway point, you have to get halfway from that point to the door. And then from where you are, you have to get halfway from there to the door, and halfway to the door, and halfway to the door, and halfway to the door. And you have to do this infinitely many times. Well, you're a finite human being. You can't do anything infinitely many times, so you're never going to be able to leave. So this is great. I get to talk about math and poetry, as long as I want to. I love it when comic strip artists have fun with mathematics. So this is Frank and Ernest, Great Moments in Science, the origins of Zeno's paradox. Where did Zeno get this idea? Zeno was late for work yesterday, and just wait till you hear his excuse. Okay, so I actually interacted with the artists on this comic strip. I was curious about it, and they said to me that this was the comic that they had gotten the most email about asking what it meant. And they said that their favorite response from a reader was, "I'm not sure I can agree with Zeno, but I'm willing to meet him halfway." Okay, so I want to tickle your brain just a little bit more with the infinite. Consider the counting numbers. I think often when we think about infinity, we think about just counting forever and ever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You just keep going forever and ever, right? So that's an infinite set of numbers. But I'd like you to also consider the even numbers. That list also goes on forever. You never run out of even numbers. So can we compare these two sets? Do they both have the same number of elements in them because they're both infinite? Or does one have more numbers in it than the other one? Because if you think about the counting numbers in comparison to the even numbers, in order to get the even numbers, you have to actually throw away half of the counting numbers. So is this set half as big as the one up top because you've thrown half of the numbers away? Or are they the same size because they're both infinite and infinity is just infinity? So just let that kind of float around the back of your mind. We will come back to this at the end of the talk. I have one follow-up question to this though. I'd like you to also consider a line segment. Let's think of a number line, the space from 0 to 1. How many fractions are in there? Just from 0 to 1. Aren't there infinitely many fractions? Because if nothing else, we've got a half and a fourth and an eighth. Can you see what I'm doing? Shades of Zeno. Can't we keep cutting that in half? A 16th, 1/32nd, 1/64th. We could keep doing that. There are infinitely many fractions just like that. And we haven't even talked yet about 2/3 or 9/10. There are infinitely many fractions between any two whole numbers. But now think about the entire positive number line. You've got infinitely many fractions here, and infinitely many here, and infinitely many between 2 and 3, 3 and 4, etc. So don't you have infinite groups of infinity? It's kind of like infinity times infinity. Remember I told you earlier there's not going to be a test. It's okay, so relax, okay. But I want you to think about, would the collection of all the fractions on the positive number line form a larger amount, be a larger set than all of the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and on and on. So one of the questions that I get a lot as a math instructor is, where am I ever going to use this in my real life? So I want to introduce you to a mathematician, G.H. Hardy, one of the most prominent, perhaps the most prominent mathematician of the early 20th century. And he said, no discovery of mine has made or is likely to make, directly or indirectly, for good or ill, the least difference to the amenity of the world. He was actually very proud of the fact that he didn't see his mathematics as having any application whatsoever. And before you think that that was a little bit selfish of him or a little bit unusual of him, please realize he was living through the time of World War I. And he saw mathematics being used to create military machines and to have other purposes for the military. And he certainly didn't want his work to go for that sort of a purpose. So for him, mathematics was sort of the biggest game in the entire universe. And he did mathematics for the pure love of mathematics. One of his major fields of research was number theory. He would probably be appalled to know that the work that he did is currently used for encryption on the internet. So if you buy something using your Visa on the internet, the thing that keeps that secure has to do with prime numbers, which has to do with number theory where he worked. And this is also true of military communications, that number theory is used to keep those communications secure. So I said earlier that playfulness is not the deepest connection between math and poetry because almost anything can be playful. But I do want to say that play in mathematics has a very important place. I want to tell you a little story. This is a map of the city of Königsberg. It's now called Kaliningrad. And the blue part that you see there is the river Pregel, which flows through the city. And there are 7 bridges. And back in the 1700s, people would challenge each other to go out walking and try to walk across each of the bridges exactly one time without going over one bridge more than once and without missing one of the bridges. But you know how it is when you're out walking with your friends and you're talking and you tried this the week before, you sort of don't remember, well, did we do that bridge already or was that last week, right? So this puzzle came to the attention of mathematician Leonhard Euler. And what he did is he used sort of the important elements of this, which is how things are connected. He made a diagram that was composed of basically dots and line segments, and he was able to prove that it's actually impossible to do what the people were trying to do. So that was just kind of a game, sort of a fun pastime of the townspeople. But once this came to the attention of mathematician Leonhard Euler, and he approached this and solved it mathematically, the outcome of that actually became an entire branch of mathematics, which is known as graph theory. And it has many applications in terms of city planning and just so many applications. That's one of those things where if you want to talk with me about that later, I'd be happy to talk about it. But I want to tell you that a lot of mathematics comes from mathematicians just playing around with something, and then we find that it actually has application. And I think there's a depth to the playfulness in poetry as well. So French poet Stéphane Mallarmé was talking to his friend the painter Edgar Degas. And Edgar Degas said, you know, I really wish, I'd like to try writing poetry. I have so many ideas that I want to get across. And Stéphane Mallarmé, the poet, responded to him, but Degas, you can't make a poem with ideas, you make it with words. In similar conversations, W.H. Auden, poet, would be approached by young people who were thinking about going into poetry. And so he would say to them, well, why do you want to write poetry? And if the person said, well, I just have these great ideas, I want to communicate to people, he'd usually say, it's probably not for you. But if the person said, I just love to play with words. I love word puzzles and word games and crossword puzzles. Then Auden would say to them, you know, you might want to give that a try. I think poetry might be for you. So in an encyclopedia about Auden, this is said about him. For Auden, poetry is childlike frivolity, gratuitous play, a cosmic word game, and the ultimate mystic crossword puzzle. So I think playfulness is not just a little piece or sort of a minor superfluous thing about poetry, but it's actually a pretty deep connection. So to wind up our first section, which has to do with play, I want to introduce you to the chaos game. And this is played using the corners or the vertices of a triangle. You label one of them 1 or 2, another one 3 or 4, the other one 5 or 6. And then you put a dot on there randomly. You just put a point in there randomly. But then what you do is you roll a die. And whatever number comes up, you put another dot then halfway between the previous dot and the vertex that's labeled with that number. So we'll go ahead and put that next point in there. We'll roll the die again. We got a 3. So now we're going to go halfway from this point to this corner here. And we just keep repeating this. Roll the die again. We get a 4. We're going to go halfway from our last dot to the 4. We roll a 6. Halfway from that last one to the corner, the vertex labeled 6. Do it again. We roll a 1. We go halfway from there up to the 1. So what I'd like you also to keep floating in your mind until the end of the talk is, if we were to do this 10,000 times, what would the result look like? Would it be a completely filled in triangle? Would it be a chaotic mess? The name of it is the chaos game after all. Or would maybe just this left-hand side of the triangle have dots in it, because we're doing this halfway thing, right? We're going halfway all the time. So just something to think about. So moving on to the next connection, which is pattern. Mathematics has actually been defined as the study of pattern. That is a definition of mathematics. But there's also a lot of pattern in poetry of many different types. We'll be focusing on rhyme. Not all poetry rhymes. But I only have an hour with you guys, unless Zeno was right and you can never get out the door, in which case I'll extend my talk. But so we're going to go back to that limerick. There was an old man of the Dee who was sadly annoyed by a flea. When he said, "I will scratch it," they gave him a hatchet, which grieved the old man of the Dee. And we're just going to take a quick look at the rhyme scheme. So we've got 3 lines that rhyme. The first 2 and the last, Dee, flea, and Dee. Now, if you were in an English class, something you might do to show the structure of this poem is to just represent those lines with an A, because they all rhyme with each other. So we're just going to label them with the same letter of the alphabet. And then if you look at the 2 lines that are left, scratch it and hatchet, those also rhyme with each other. And so we're going to represent those with a different letter because they don't rhyme with the other lines. So the rhyme scheme of a limerick is AA, BB, A. There's another form of poetry that's actually my favorite. It's called a villanelle. And I know you can't read that, it's too small, but I just wanted you to see the overall structure. That it has 6 stanzas, that the first 5 have 3 lines each, and the last one has 4 lines. So we will go ahead and go through this poem. Before I do, I just want to share a little bit about it. This was written by Dylan Thomas. He wrote it when he found out that his father had been diagnosed with terminal cancer. So he was writing actually to his father. Do not go gentle into that good night. Old age should burn and rave at close of day. Rage, rage against the dying of the light. Though wise men at their end know dark is right, because their words had forked no lightning, they do not go gentle into that good night. Good men, the last wave by, crying how bright their frail deeds might have danced in a green bay. Rage, rage against the dying of the light. Wild men who caught and sang the sun in flight, and learned too late they grieve it on its way, do not go gentle into that good night. Grave men near death who see with blinding sight, blind eyes could blaze like meteors and be gay. Rage, rage against the dying of the light. And you, my father, there on the sad height, Curse, bless me now with your fierce tears, I pray. Do not go gentle into that good night. Rage, rage against the dying of the light. So there is a lot of repetition in there. There's a lot of rhyme. There's a lot of patterning. In this poem, we actually see entire lines repeated over and over again. Do not go gentle into that good night. Rage, rage against the dying of the light. And so I've highlighted those using color here. In the first stanza, you see both of these lines. One is the first line of the entire poem. The one is the last line of the first stanza. And then in the succeeding stanzas, you alternate between those as the last line of the stanza. But when we get to the end, then you take both of those lines and you put them together at the very end of the poem. So that is the structure of a villanelle. And I don't know, I find that a very beautiful form of poetry. There's so much echo involved with that. Okay, so I'm looking at the rhyme scheme here, and the reason that I used a capital instead of a lowercase is that these lines are repeated in full. That was the do not go gentle into that good night, and rage, rage against the dying of the light. So it's not just that they rhyme at the end, but you're going to be using the entire line in full over and over. So we use a capital letter there, and those are different from each other. So one is A1 and A2. Old age should burn and rave at close of day. That rhymes with other things within the poem, but it's not repeated in full, so that's just represented by the letter B. So just some patterning representation in poetry. I use patterns all the time in mathematics. One of the things that students struggle with, particularly when they're in, say, a pre-algebra class, is what it means to subtract a negative number. What does that mean? And why does it work? What is that? So I often fall back on patterns to help them out. And I start out with something they're familiar with. So 6 minus 4 is equal to 2. They know that. They've known that for many, many years. Let's start to build a pattern out of that. Let's do another subtraction problem. How about this time 6 minus 3 and 6 minus 2? So on the left-hand side, I've got all 6s. On the right-hand side, we're going up 1 each time, right? 2 and then 3 and then 4. But in the middle, you're going down 1 each time, 4 and then 3 and then 2. One of the things I sometimes say with subtraction is when you subtract less, you're left with more. So if you have a plate of 6 cookies and somebody eats 4 of them, you don't have very many left. But if they only eat 2 cookies, then you have more left, right? If you subtract less, you're left with more. So let's continue that pattern on the right. The next number should be a 5. If we continue our pattern in the middle, we should have 6 minus 1 next, and that in fact is equal to 5. So let's continue filling things in over on the right-hand side. And if we continue the patterns the rest of the way, yep, 6 minus 0, that equals 6. That works. So we just keep checking. Yes, that works. Yes, that works. Well, if this is the case, the next number I'm going to subtract is a negative 1. And the next number I'm going to subtract is a negative 2. So 6 minus negative 1 is 7. 6 minus negative 2 is 8. When you subtract less, you're left with more. Okay. Let's look at another pattern that's just kind of a little more playful and fun. This is a pattern that starts out with a triangle of 1s. I think of it as something that a child may have come up with on a long road trip. Maybe during my childhood. I think all kids these days have cell phones, right? And they're playing something rather than drawing things like this. But anyway, a child, I think, could have come up with this. Make a little triangle out of the 1s, and then let's just continue the 1s down one side and down the other side, but it's kind of boring to just have 1s in there. So let's start filling in the middle. And we'll do that by adding the 2 numbers that are above. For instance, you see where the 2 is, and above the 2 we have 2 1s. 1 plus 1 is 2. So now we're going to add 1 plus 2 and get a 3 here, and we'll fill in the rest of this thing. This is actually known as Pascal's triangle. And let's check out some of the patterns in here. So if you look at that diagonal that the arrow is pointing to, we see the counting numbers. So counting numbers are one of the patterns in here. Looking at the next diagonal, we see 1, then 3, 6, 10, 15, 21, Does anybody see what's happening? That's a little bit harder of a pattern.
2, 3, 4, 5, 6 being added.
2, 3, 4, 5, 6 is being added. So you are adding consecutive numbers. Yeah, absolutely. So 1 plus 2 is 3, but then if you add 3, you get 6, add 4, you get 10, add 5 to get the next number, add 6 to get the next number. So we should have a 28 down here because 21 plus 7 is 28, which, oh, yeah, we see from this pattern as well that that should be the case. There are all sorts of patterns in here. If you think of a number in the center, like I've indicated here with the circle, and you look at the numbers that surround it, and you take every other one, and you multiply them, you'll get the same number each way. So let me explain that a little bit better. So if you see where the black arrows are pointing, I have a 1, a 5, and a 6. 1 times 5 times 6 is 30. But then these are green arrows here. So 3 times 1 times 10, oh, 3 times 1 times 10, well, that's also 30. So if you alternate the numbers that you multiply, you'll get the same number, and that is true throughout this triangle. This triangle has to do with something else. It's very closely involved in probability. And so as an example, my husband and I have 3 children. They are all boys. If we had known that we were going to have 3 children, we could have figured out what our probability was that they would all be boys. All boys, BBB. But we could have had 2 boys and a girl, but the girl could have been born 3rd or 2nd or 1st. We could have had 2 girls and a boy, same thing there, girl the youngest, girl in the middle, girl the oldest. Or we could have had 3 girls. Okay? So if I'm talking about probability, there are 8 options up there, and I got the boy, boy, boy option. Okay? But there are 3 ways in which to get 2 boys and a girl, so that's a 3 in 8 chance, 3 in 8 probability. 3 ways to get 2 girls and a boy, and 1 way to get 3 girls. So the numbers that we're seeing there are 1, 3, 3, 1, and 8, which is 1, 3, 3, 1 added up. You see that there are 8 of these things in blue. Well, how does that relate to the triangle? If we look for these numbers in the triangle, 1, 3, 3, 1, we find them right there in that row. And if you add those numbers, you get 8. Well, as long as we're adding numbers across a row, let's just do that for all of the rows. Oh, I get 1 and 2, 4, 8, 16, 32. It's doubling all the way down. So there's just pattern after pattern after pattern inside of this thing. Going a little deeper with the mathematics to see something else it's related to. If I asked you to expand x plus 1 to the 5th power, what you would need to do is multiply this by itself 5 times. My students aren't super happy when I put this on the test, because guess what? That's a lot of work. I'm going to show you what the work looks like. Okay? So first, yeah, I just heard, oh. That's what my students say too. Okay, first you're going to multiply these together and simplify. Then you're going to multiply by this one, simplify that. Then multiply by this piece. Woo, you got a lot of terms there. Simplify that. Multiply by this one, you get all of those terms. Simplify that. So here's the answer down at the bottom in a box. I'm going to put the answer back up a little bit neater. There's the answer. And I'd like you to look at what we call the coefficients. Those are the numbers in front of the variable. We get 1, 5, 10, 10, 5, 1. If we look at our triangle, we see that there's a row that has 1, 5, 10, 10, 5, 1. This is not a coincidence, by the way. If I had asked my students to raise that to the 6th power, these would be the coefficients. Those would be the numbers you're seeing in front of x. To the 7th power, here are these. So math is full of shortcuts, and patterns give us those shortcuts. So I'd like to do one more thing with Pascal's triangle. You'll notice I've taken the numbers and I've put them into little hexes, because what I'd like to do is compare like where the odd numbers are compared to the even numbers. Is there a pattern in that? So I printed this out, I got a marker, and I started coloring in all the odd numbers. And look at what I came up with. Very symmetric, you know? Kind of a cool pattern. If I had actually taken this, I think the next one is 32, 64, I think 64 rows. I didn't generate this one, I got it elsewhere. That would have been a lot of coloring, a little tedious. If you go to 256 rows, okay, the pattern continues, right? We can see a pattern there that you're seeing all over the place in smaller detail in various places. Okay, so continuing to talk about pattern, I'm going to get back into poetry. We've been on math for a while. Maybe it's time to look back at poetry. The next poem is Robert Frost's Stopping by Woods on a Snowy Evening. Whose woods these are, I think I know. His house is in the village, though. He will not see me stopping here to watch his woods fill up with snow. My little horse must think it queer to stop without a farmhouse near, between the woods and frozen lake, the darkest evening of the year. He gives his harness bells a shake to ask if there is some mistake. The only other sound's the sweep of easy wind and downy flake. The woods are lovely, dark and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. So this is a little different. Oh, I got ahead of myself. Wasn't looking at my slides. This has a little bit of a different rhyme scheme than the others. You'll notice that three words in each stanza rhyme with each other. Here we have shake, mistake, and flake. And then there's a third one that doesn't. Let's back it up one more. Here we have no, though, and snow, but then we have here. That doesn't rhyme with anything else. Down here we have queer, near, year, and we have lake, which doesn't match anything in that stanza. But what's happening is that that line that ends with a word that doesn't rhyme with anything else in the stanza rhymes with three words in the next stanza. So we have here, and that rhymes with queer, near, and year. And then we have lake, and in the next stanza we have the words shake, mistake, and lake. Sometimes patterns can point to something deeper. Sometimes they don't. I want to propose to you something that I've heard said about this poem. This may or may not be correct. It may or may not be what the poet had in mind. But remember that he had called this the darkest evening of the year. And he says in the first line here, the woods are lovely, dark, and deep. Then at the end, of course, you don't have a next stanza to link that third word to, or the end of the third line to, so these all rhyme with each other, and he's just repeated the line for the last two lines of this stanza. But some people say that rather than that just being convenient, it just worked out well, that he's actually saying something further, and he's not talking about just snuggling up in a cozy bed, but he's talking about the sleep of death. So listen to this one more time. The woods are lovely, dark, and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. You can think about that, whether you think there's something more in there in that haunting echo, or if that's not the case. So jumping back to mathematics, some more patterning, some more echoing. We're going to work with some geometrical shapes. We've got a triangle, but we're not just going to leave it static. What we're going to do is find the midpoint of each side and connect those midpoints. That creates an inverted triangle in the middle, and we're going to remove that. This is a process that we're going to repeat over and over. So this is known as the Sierpinski gasket. And so if we take the shape that we have up there, you'll notice that we have three triangles remaining. We're going to do this same process in all three of those triangles. Take out the center inverted triangle. Now we have 9 triangles left. We're going to run through that same process again and then again. This is a shape that's known as a fractal. Technically, it's not a true fractal until you have done this process on it infinitely many times. If you go quite a few more stages along, this is what it looks like. Does that look familiar? It's also what we got if we colored in all the odd-numbered cells of Pascal's triangle. So I find that kind of surprising that there's a connection there. There's also a shape that's known as the Sierpinski gasket, or carpet, excuse me. This one starts with a square instead of a triangle. You cut it up like a tic-tac-toe board, and you take out the center. So instead of having one square, like we do right here, you now have 8 squares around the outside that are left. You're going to repeat this same process on those 8 squares, and then you're going to repeat it again and repeat it again. And once you've done this many, many times, what this looks like is that. So again, these 2 shapes are called fractals, the Sierpinski gasket and the Sierpinski carpet. They have some surprising properties. One property is that for each of these, once you have the full fractal, you've run this infinitely many times, there's no area left at all. But the perimeter is infinite, which may seem kind of unusual, but this type of geometry, it's been called a new geometry of nature. This might not look very natural, but it's a way that things in the natural world operate. For instance, think of your lungs. Your body, your circulatory system picks up the oxygen on the surface of your lungs. So you really want to maximize the surface area of your lungs. But your lungs are only one organ of many that you have in your body, so they're limited in terms of volume. If you think of what your lungs are like, you've got your trachea into the bronchi, into the bronchioles, into the alveoli. It's branching. Think of a tree outside, right? So smaller parts look like larger parts, and it just keeps repeating. And this is how our bodies and other things in the natural world are able to minimize certain properties and maximize other properties. These are known as linear fractals. There are also fractals that are known as nonlinear. Instead of doing a repetition on a shape, we're going to do a repetition on an equation. Just want to remind you guys, we are covering a lot of different ideas really, really fast. Remember I told you at the beginning we were going to do that there's not going to be a test at the end, and just kind of take it in and have fun with it. Check out this beautiful image. And we're going to do something here that's called zooming. We're going to zoom into this shape. So the thing that'll come up first will look a little bit like a snowman on its side. And we're just magnifying it, magnifying it, magnifying it. This is also a fractal. It's a different sort of a fractal than the other ones. Do look for natural shapes. Notice this looks like the original shape. It is similar, but it's not identical. It's not exactly the same. So there's this property of self-similarity. You know, can you see things that look like seaweed, or maybe the tail of a peacock, or I don't know, a fern frond? Just different natural shapes. So fractal geometry is something that can be used to study the jaggedness and the roughness of what's really out there in the world. And by the way, we could magnify this forever, and we would never lose detail. We would keep seeing new detail. So this is a very complicated shape. It is not a piece of art. It is a graph. It is a mathematical graph. So think about what kind of an equation might allow you to graph something like that. What must that equation look like? Well, when we get down in here, that always kind of makes me think of neurons in the brain or something. But that's just a light connection. It's just what I'm seeing in this. Okay. And as I said, we could keep magnifying that forever, but I do only get you for an hour, so we need to keep going. And sometimes it doesn't want to move away from that slide. There we go. That's actually the equation that gives rise to all the complexity that you were seeing there, infinite complexity. Okay, so it has only 6 symbols. It's a mathematical equation. Notice the equal sign looks kind of funny. It's because you're going to find a value and then plug it in again, then find a new value, plug that in again. It's something that's called iteration. Okay. So we've talked about playfulness, we've talked about pattern. The next connection that I see between mathematics and poetry is power. If we can take something that small and use it to create something that complicated, I would say that that's a pretty powerful thing that we're able to do. Mathematics is a shorthand, and you know about these things that we can write in a briefer way. Instead of adding 3 to itself 7 times, you could just write that as 7 times 3. We can capture that more briefly. Instead of multiplying 3 by itself 7 times, we could say, well, that's 3 to the 7th power. We can even do some more interesting things, like multiply 1 times 2 times 3 times 4 times 5 times 6 times 7. The notation for that is a 7 with an exclamation point, which is known as 7 factorial. The next slide should have a word problem on it. Don't read the whole thing. We're not going to take the time to read the whole thing. But here's a word problem. It's from a famous mathematician by the name of Al-Khwarizmi. We get our word algorithm from his name. An algorithm is a process or a method for doing things. And so one of the elements of mathematics that makes it so powerful is our ability to take something like this and turn it into something like that, which we can manipulate and we can use to solve. If you've had beginning algebra, you know that you can subtract the 39 from both sides, you're going to factor, and you're going to solve from there. So it gives us the power to do that manipulation. So math is a language that has this sort of shorthand, and that brevity gives it its power. And I see the same thing in poetry. This is a poem by Emily Dickinson. She had already lost 2 family members to death, and this was written after a 3rd family member had died. So I never lost as much but twice, and that was in the sod. Twice I have stood a beggar before the door of God. Angels twice descending reimbursed my store. Burglar, banker, father, I am poor once more. And I'd like to draw your attention to that second to last line. It only has 3 words in it: burglar, banker, and father. Notice that there's a comma between burglar and banker and a dash between banker and father. So if you think about the grief process, there's denial and anger and bargaining and depression and acceptance. And as you read through those words, I think you see those pieces. Her first word in that line is burglar. She's mad. This loved one has been stolen from her. And then the next word, banker, banker is somebody you could bargain with. Please let this be a dream. I promise I'll be good for the rest of my life. Please don't let this be real. And then after a longer pause, signified by this dash, we have the word father. So she is at a place of acceptance. And I would say, too, that this demonstrates her relationship with God. She's angry at him, then she wants to bargain with him, and then she's back in relationship, and it's a prayer. Father, I am poor once more. I go back a second. Over the years, I have found that not everybody has a dark side like I do. You'll notice that a lot of the poetry I've put up here has to do with the theme of death. I think poets do a really good job of exploring that theme and helping us to come to terms with it and grasp it and maybe be at peace with that. So I want to put up a poem that's a little happier after this one. So this one is by E.E. Cummings. May I be gay like every lark who lifts his life from all the dark, who wings his why beyond because and sings an if of day to yes. And what I'd like to focus on are the words if and yes that are used to describe day. Think about that. So I'm just going to compress the whole poem. May I sing an if of day to yes. And I don't want to really break that down too much and talk about what the if means and what the yes means. I think that you can probably pick up on that, the difference between an if of day to a day that is yes. Okay? So a lot of power in both mathematics and in poetry. And at this point, we're going to transition to what is the trickiest for me to try to get across. So we've talked so far about playfulness, pattern, and power. But what I'm moving into now is what I think is the deepest connection, and that is elegance. And that is a really hard thing to get across. As they say, beauty is in the eye of the beholder. So what I find beautiful, probably someone else may not find beautiful. This is back to mathematician G.H. Hardy again, who was quoted earlier. He wrote, "A mathematician, like a painter or poet, is a maker of patterns. The mathematician's patterns, like the painter's or the poet's, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics." Okay, so my experience, I love poetry. I try to write poetry. I don't do so well with that, but I try. My experience of writing mathematical proof and trying to write poetry is very similar. You're trying to say something, you want to do it as briefly as possible, you want to do it elegantly and in sort of a clever way. So there's an elegance to both of these things. We're going to start with poetry. I've got a couple more negative poems for you, but I'll throw in some more positive ones later. I'd like us to compare these next two poems. The first one is called Rhetoric. "Hello there, how do you do? Why, I'm just fine, and how are you? Fine, thanks, have a jolly day. Why, thank you, and the same to you. Both these lives are filled with pain, and neither knows it. What a shame." So that's Rhetoric. The next poem is called Not Waving but Drowning. "Nobody heard him, the dead man, but still he lay moaning. I was much further out than you thought, and not waving, but drowning. Poor chap. He always loved larking, and now he's dead. It must have been too cold for him, and his heart gave way, they said. Oh, no, 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 it was too cold always." Still the dead one lay moaning. "I was much too far out all my life, and not waving, but drowning." Now, I chose to pair these two poems because I know they say the same thing. I wrote the first one. And when I came across this one a few years later, I felt like I'd been run over by a freight train, because this said exactly what I wanted to say, but in a way that I lacked the art to say it. Through the use of the metaphor of waving, right? Somebody's waving their arms. Are they, greeting you and happy? Or are they desperately, needing to be saved? They are drowning. This poem is by Stevie Smith. It's been published in many, many anthologies. And as I said, the other poem was by me. Okay, so going to mathematics, I'm going to give you a little puzzle here. So we have an equilateral triangle on the outside, an equilateral triangle on the inside, and then a circle between them. So a circle inscribed in that outer triangle, and then a smaller triangle inscribed in that. And the question for you is, what is the size of that smaller triangle in the center compared to the larger triangle on the outside? How do they compare in terms of ratio? Well, there's a way to do this using geometry and algebra, and I have it all written out. I'm going to go ahead and show that to you. That's what it looks like. There's some information here you need to have, such as a line tangent to the circle is perpendicular to the radius at the point of tangency. And you need to know things like the relationship between the sides of a 30, 60, 90 triangle. And if you put all those pieces together, with any luck, you come up with the correct answer of 1/4. Okay, so the smaller triangle in the center is 1/4 the area of the larger triangle on the outside. Does that look like fun? Maybe let's try a different approach to this. So let's look back at the original. And I want to do something instead that's called recasting, or in other words, changing your point of view. Let's take this circle in the center and spin it. Let's rotate that a little bit. Can you see it? There's one triangle up on the top, another one on the bottom left, another one on the bottom right, and there's one in the center. So, compared to the outer triangle, that inner yellow triangle is 1/4 of the size. To me, this is more elegant, it's certainly more clever, and I think it gets more to the heart of the matter. Okay, so that's an important or helpful mathematical problem-solving technique, is to recast. In other words, look at something from a different point of view. But when I think about elegance in terms of mathematics, I'm typically not thinking of a puzzle or a problem. I'm thinking of a proof. So here we go. I'm going to talk with you about a proof having to do with prime numbers. First, I'll give a quick review about what prime numbers are. Those are the numbers that do not have any factors other than 1 in themselves. 1, by the way, is not prime. Primes have exactly 2 factors, like 17 is 1 times 17, 2 different factors. So those are the first few prime numbers. The question is, does that list go on forever, or is there some biggest last prime number somewhere? So we're going to explore that a little bit. How many primes are there? Do they stop after a while, or do they keep going? Well, if we look at the first 10 numbers that could potentially be primes, because 1 doesn't count, we start at 2, we've got 5 of them there in the first 10 that are possible. In the next set, going from 12 to 21, we've only got 3 primes. Going from 22 to 31, we've only got 3 primes again, and in our next set of 10, we actually only have 2 primes. So it looks like they're kind of thinning out, which maybe makes sense because the further you go, the more numbers you have less than the number you're looking at that might divide into it. Looking at it a different way, of the numbers that could be prime below 10, 4 of them are. So 10 through 9, or 2 through 9, there are 4 primes. So it's 50% of the numbers below 10 are prime. Under 100, 24% of the numbers are prime. Under 1,000, we only have 17% of the numbers up to 1,000 being prime. If we push it to 1,000,000, only 8% of the numbers from 2 to 1,000,000 are prime. So it really looks like they're thinning out and that we're running out of them. So this question of whether the prime numbers are infinite or not goes back to the time of Euclid, and he was able to prove one way or the other. And it turns out that there are infinitely many primes. So the next thing I'm going to put up is his proof, but I've done it in mathematical language, modern mathematical language, because I wanted to show it to you as briefly as possible, because that's part of the power of mathematics. So that's what, this wasn't the proof that Euclid wrote, but that's what it looks like in modern terms. I'll talk you through it a little bit. If you want to know more, see me afterwards or come by my office. But basically what Euclid did was say, suppose there exist a finite number of primes. So you have the first one, second one, third one, all the way up to p sub r, which is the very last prime. Then he uses those to create another number, and he points out that if you follow the reasoning, that number has to be prime and it has to be composite, which is a contradiction. And that's what those 2 arrows pointing at each other mean. Because of this, there are infinitely many prime numbers. This is called a proof by contradiction. This type of proof has been around for a long time. It's also called reductio ad absurdum, or reducing to absurdity. So this is kind of a surprising thing. He starts out by saying, okay, fine, let's just say they stop. Oh, well, if we follow that logic, we find out that we get a contradiction and they don't stop. So this brings me to the last part of the talk, which is surprise. We're going to lighten things up here. So we've looked at playfulness, pattern, power, elegance, and now we're going to look at surprise. Although to finish off that section, I just want to mention that Samuel Taylor Coleridge defined poetry as being the best words in the best order. I would say that mathematical proof is the best statements in the best order. So just another connection there. So looking at poetry in terms of surprise, I'd like to share a little bit about Dorothy Parker. Lived from 1893 to 1987. She was a member of the Algonquin Round Table. She was a poet, she was a screenwriter, she was a critic. She did many, many things having to do with writing. And in one book review, she said the following: "This is not a novel to be tossed aside lightly. It should be thrown aside with great force." Okay, she was a very witty woman, but she was not a very happy woman. In fact, she attempted suicide many times, so here we go into some dark poetry again. Here's her poem, which is known as Resume. Rivers pain you, excuse me, razors pain you, rivers are damp, acids stain you and drugs cause cramp, guns aren't lawful, nooses give, gas smells awful, you might as well live. Okay, we'll lighten it up a little bit. The next one is by Edna St. Vincent Millay. This has to do with a relationship. She says, and what are you? That missing you, I should be kept awake as many nights as there are days with weeping for your sake. And what are you that missing you as many days as crawl? I should be listening to the wind and looking at the wall. I know a man that's a braver man and 20 men as kind. And what are you that you should be the one man in my mind? Yet, women's ways are witless ways, as any sage can tell. And what am I that I should love so wisely and so well? And one more poem here. This is by Pete Hine, who is actually also a mathematician. It's called The Egocentrics. People are self-centered to a nauseous degree. They will keep on about themselves while I'm explaining me. Okay, so some irony, a little bit of surprise in poetry. So I want to come back to the chaos game. We're going to wind things up here in a few minutes. Think through, are you thinking that this is going to be a chaotic mess? Is the triangle going to be completely filled in? Is it only going to be on half? So this is something some students put together for me quite a few years ago when I taught a class on fractals. So this is going to actually run a simulation of the chaos game using a random number generator on a computer. It's going to fill in pretty quickly. Do you see anything you recognize developing there? Okay, totally different setting. We saw this with Pascal's triangle when we colored in the odd-numbered cells. We saw this with fractals when we did the Sierpinski gasket. And here we're playing a game by rolling dice and dealing with randomness, and we come up with this same shape that we've seen twice before. So I have a question for you. If you were to play the chaos game on a square, and we labeled the vertices, the corners, 1, 2, 3, 4, and I don't think I want to use a 6-sided die. I think there are enough gamers out here today that know that there are other sorts of dice that exist. We might want to use this one in the middle that has the numbers 1 through 4 and roll that. And we would do the same thing, right? We would put a point on here randomly, we'd roll the die, we'd go halfway from our original point to the number that's indicated, and on we go. Any guesses about what's going to come up?
Carpet.
The carpet. All right, that thing. Actually, the surprise is what you get is a completely filled in square. Thank you for your bravery. I appreciate that. This doesn't work so well if nobody shouts out, so thank you for being brave. So there was one other question that I asked you guys, and that had to do with infinity, and whether or not there were more counting numbers than there are even numbers, or if the sets both have the same amount of numbers in them because they're just both infinite and infinity is infinity. And then I pushed it one step further and I said, well, what about all the fractions on the whole number line compared to the counting numbers? Are there more fractions? Because you've got infinitely many fractions in between each counting number. And so I'm going to give away the answers to this. I'll put some resources up here in a second. They're also on your paper in case you want to go deeper. But they're actually the same amount of even numbers as there are counting numbers. There's the same amount. Even though you've thrown away all the odd numbers, even though you've thrown away half of an infinite set, the same level of infinity still remains. Strangely enough, the same thing is true with the fractions. There are not more fractions than there are counting numbers. There are the same amount. It's the same level of infinity. So that's kind of surprising because it seemed like the fractions were infinity, times infinity. However, there are some other points on the number line that can't be written as fractions. A famous one is pi. Sometimes in elementary school they have you write pi as 22/7, but it's not exactly equal to that. It's not exactly equal to any fraction. It's called an irrational number. You might know of one or two others. There's e, which is the Euler number, 2.718. It has to do with compound interest and many, many other things. Square root of 2, 1.414, and the decimal keeps going. That also can't be written as a fraction. So what do you think if I throw all the decimal numbers on there as well as all the fractions? You have a higher level of infinity. That also is an infinite set, but it's bigger. It has more things in it. So that's the surprise there. I think a couple of surprises there. So if you want to go deeper, often when I talk with people about infinity or fractals, they do get intrigued and they feel like, well, how can I find out more? That kind of just went over my head, and I'd like to know a little bit more. These books are both very accessible and very fun. This book on fractals is just full of stunning pictures, and it ties fractal geometry into the natural world beautifully. Infinity and Beyond, written by Eli Mayor, also very accessible, a very good read. So, do I say the end, or do I say it's the beginning? If you'd like to contact me with any questions, that's my email address. Thank you so much for coming.